Hello everyone, and welcome back to NL582, Modeling and Control of Electric Machines and Drives. And this is tutorial number 5. We have just finished talking about, or actually started talking about the testing of three-phase induction motors, or we call determination of the equivalent circuit parameters of the machine. So we take the machine to the lab, perform 3 different tests. It's a DC test, no load test, and locked rotor test, and use this to find the different equivalent circuit parameters of the machine, where we can use it after that to expect the performance of such a machine. Okay, so I'll start this tutorial by trying to give you a numerical example of using that, where you get the test data of such a machine and you're required to find the equivalent circuit parameters of it, just to solidify the concepts we just had in the lecture and make it more concise. Okay, so I'm gonna write down the problem data this time. I'm saying that three-phase 60 horsepower 2200 volts 6 poles 60 hertz delta connected squirrel cage induction motor. Has the following test results, and giving you the test results like that. DC test, VDC equals 56 volts and IDC equals 30 amps. The locked rotor test, I'm giving you this data: 270 volts, 25 amps, 9000 watts, and 15 hertz. No load test, and here the data: 2200 volts, 4.5 amps, 1600 watts, and 60 hertz. And he wants you to calculate the equivalent circuit parameters along with the combined core and rotational losses. Okay, so here the data you find for this machine. Okay guys, so it's giving you that machine is 3-phase, obviously 60 horsepower. So we know that the data is given at the very beginning of the problem of the rating of the machine. Okay, those data that the machine designed to work at all the time without having a problem actually. So the machine has 3-phase 60 horsepower, and a horsepower is a measuring unit. Okay, let me just remind you of that. So the horsepower equals 746 watts. Keep that in mind. Okay, so that's a unit to measure the power of motors. So whatever you wanna just find it by the watts, you just multiply by 746, you get the equivalent watt of it. So yeah, so this should be 60 multiplied by 746 watts, and if you're given like watts and you want it in horsepower, you just divide it by 746. So it's just a unit for measuring the power of the motor. Okay, So that is the rated output power of the motor. So this guy 60 horsepower here is P output rated. 2200 volts, and like we said last time, that is the line-to-line voltage, also rated. By default is giving you, so the given voltage is the line-to-line volts by default. Okay. 6 poles, so the number of poles is 6, 60 hertz, delta connected, so the connection is delta, keep that in mind. If he doesn't give you the connection, so the default connection is Y connection, so he is here determined as to be delta connection. Squirrel cage, and that's good to know. So squirrel cage induction motor have the following test results and giving you the results for each test. For DC test, giving you the DC voltage and current measured. For the rotor test, he's giving you the voltage, current, power, and hertz. Like you've seen here, the frequency of the log rotor test is not 60 hertz. Rather, it's reduced frequency, like we said in the lecture. That is usually doing at a reduced frequency just to account for that the frequency of the rotor is much less than its actual value. When you just, in the real life, it is the frequency of the rotor equals SFS. So it's all the time very small compared to the frequency of the stator. So to be more realistic with the log rotor test, we just do it at a reduced frequency if it is available in your lab that you have a variable frequency supply. Okay, so for this guy doing this, he have a variable frequency supply and he performed the log rotor test at 15 hertz. If it's not given in the problem, then assume he does not do anything about the frequency and he's just doing the log rotor test also at 60 hertz. But since it's given here to be 15 hertz, then you stick with the 15 hertz given. Okay, guys? For the no-load test, is giving you also the voltage, current, power, and hertz. Obviously, the no-load test is done at the rated frequency, which is 60 hertz, because don't need to do anything about it here. Okay, but look at this to keep in mind. As we said before, the voltage which the no-load test is done at is the rated voltage, V rated, and the current where the log rotor test is done as is the rated current. Okay, so the problem does not give you this information. You can give you the no-load test without the voltage because you know to yourself that is the rated voltage here. You see? So the rated voltage given the information of the machine at the beginning is 2200 volts with the same volts of the no-load test. So if it's not given in the test results, you know to yourself from the ratings of the machine. The same like the current here. If it's not given, it can be found from the ratings of the machine. The machine, you have here the power and the voltage, okay? So if it's not giving you this current here in the test, he will giving you the power and voltage of the ratings of the machine and also the power factor. Then you can use the power equation P equals 3 VI cosine phi to find the missing current. This current will be the rated current will be used in the log rotor test. Okay, guys? So it's given here, that's good, but he may not give it to you, and this will be okay also because you know to yourself that the log rotor test current is I rated. Okay, guys? Sounds good. The very good information here, he's found you to calculate the equivalent circuit parameters along with the combined core and rotational losses. That means he means that the core losses is combined with the rotational losses as a constant loss, and that means we are using the approximate equivalent circuit. Okay, if he didn't say that, that means you cannot use the approximate equivalent circuit on your own. You have to use the exact equivalent circuit, guys. So the approximate equivalent circuit is a little bit less accurate compared to exact equivalent circuit where you have RC in the circuit. Okay, so that's using approximate equivalent circuit, neglecting RC. Keep that in mind, that's important. So we don't use this until you're told to do. Like this, he's saying the combined core and rotational losses, or he just give you using the approximate equivalent circuit or something like that. Otherwise, if it didn't give you any clue to use the approximate equivalent circuit, you stick with the exact one because that's the default you can use. Okay, guys? But here, this is approximate equivalent circuit and it's much easier. Okay? So we're using here the approximate equivalent circuit. So draw it for yourself. That's all the time useful. Here it is JXM, which is the only shunt element because we don't have our C here because that's the approximate equivalent circuit. So it is JX2, and here is R2 over S. That is V1. Okay. And now remember that is the pair phase equivalent circuit, so everything here is pair phase quantities. Okay guys, so let's play this. How to find the equivalent circuit parameters? Just follow the same procedure we have in the lecture. So we start all the time with the DC test, okay, performing the DC test like we said. So the machine here is connected like delta, he said that. So here's your connection. You have three-phase winding and the stator, each one with the same resistance because they are all balanced, yeah? And you perform the DC test like between any two terminals, and you apply the voltage that is VDC given to you, and that is the current IDC moving through here. Okay, like we just derived back, that if you divide VDC over IDC, that will give you the equivalent resistance seen by this DC source here, which is basically 2R1 in parallel with R1. Okay, so that's like we said in the lecture, will just land out will be 2 over 3 R1. So if you want to find R1 DC, it will be 3 over 2 VDC over IDC. Okay, so it is 3 over 2 VDC given, and the results 56 over the current IDC given also 30 to be 2.8 ohms. Like we said, that is the DC value. We should multiply this by the skin effect factor 1.15 to 1.25. But as I said, if it's not given anything to talk about it in the problem, you just ignore it, and that is the resistance you just can use. Okay, so that is the R1 from DC test, and we can proceed. So after the logged rotor test, we go from DC test, we go directly to the logged rotor test. Sometimes by the way we call it the blocked rotor test. They are the same. Okay, fine. So for the logged rotor test, as we know, the speed equals 0, and that means your slip equals 1. Like we derived, the equivalent circuit will look like that. R1 JX1, that is the stator, and that is JX2 and R2 over S here equals 1, and you don't have the shunt element JXM because, like we said in the logged rotor test, it will be ignored here because, you know, R2 plus JX2 is now very small compared to JXM, and they are connected in parallel, so this JXM here is very high compared to those guys JXM and R2, so this can be just ignored. Okay, so we can just take it out here without losing accuracy. Okay guys, okay, so here is the voltage applied, which is V logged rotor, and the current going here is I logged rotor. All the time, don't forget, that's pair phase circuit. Everything here is pair phase, okay? And all the voltages and current given to you is line to line by default unless something else is said. So before doing anything, make sure to do your conversions, okay? So the V logged rotor will equal the given value, and the logged rotor test data given here is 270 volts. Okay, that is the given one, 270 volts. Keep in mind that is delta connection, and that means V phase equals V line to line. Okay, so the phase voltage here equals the line voltage, the same value, we don't play with it, that's good. But for the current I logged rotor, the given value is 25, so I'm going to take this 25 and divide it by square root of 3 amps. Okay, why? Because for the delta connection, the I phase which you want is I line to line divided by square root of 3. So the given value by default is a line value, so you divide it by square root of 3 to find the current. If it is a Y connection, it will be the opposite way. The line current equals the phase current, but the phase voltage is the line voltage given divided by square root of 3. So don't get confused, just do those online. Okay guys, okay, and now we can just do it. You just say that the P log rotor here from this circuit, you just have two resistances, so the active power dissipated in those resistance will be 3I log rotor square for the total resistance here, which is R1 plus R2. Okay, that's good. Now substitute. P log rotor that's given to you is 9,000, that's given in the question, equal 3 times I log rotor, like we said, is 25 divided by square root of 3, and it's all squared. R1 plus R2. R1 found from DC test to be 2.8 plus R2. Everything here is just known except for R2. So R2 here can be found to be 11.6 ohms. Okay. And that is your second parameters. Second parameter here just found from the log rotor test. That is R2, guys. Okay. Okay. And now let's move on. Okay, so moving forward, we need to find Q. Okay, so the reactive power and the log rotor test here, we need to find it before we go any further. How to find this? Go back again to the active power equation. P log rotor will equal square root of 3, or yeah, just let me do it all phase again, not confuse you. 3 V log rotor I log rotor cosine theta log rotor. Okay, so the P log rotor given is 9,000, that will equal 3. V log rotor, as we find it, 270. I log rotor as found is 25 over square root of 3 multiplied by cosine theta log rotor. So everything is now known. You can find theta log rotor easily to be 39.664 degrees. Okay, that's good. And if you remind yourself by the power triangle, so that is P log rotor, here is Q log rotor, and here is theta log rotor. Okay, so from this you can find Q log rotor easily by multiplying P log rotor of 10 theta log rotor. Okay, and this will give you 7,462.406 volt ampere reactives, VARs. Okay, guys? And from this, you can say just the Q log rotor again from the circuit we just landed here. The reactive power is just going to the inductors here, X1 and X2. So this will be 3I log rotor square X1 plus X2. And I'm going to say that X1 plus X2 log rotor, okay? So the Q is 7,462.406 equal 3 I log rotor 25 over square root of 3 squared multiplied by X1 plus X2 log rotor. So your X1 plus X2 log rotor will equal here 11.9398 ohms. Okay? But don't forget, that is given at frequency that's given in the problem here of the log rotor test, and he's done this at 15 hertz, not at 60 hertz. And you want them to be at 60 hertz because your equivalent circuit, all of it works at the rated frequency, which is 60 hertz. So the actual or the rated X1 plus X2, we call it rated values, will equal X1 plus X2 log rotor, which you just calculated, multiplied by F rated over F log rotor. So this is a value we just found, 11.9398 multiplied by F rated, which is 60, over F log rotor, which is 15. So this give you 47.76 ohms. So those are the actual X1 plus X2 you want to find. Okay, guys? How to separate them, like we said, using the table given in the lecture. And as I said, the table said that, if you refer it back, if it is a wound rotor machine, then it's 50-50, but it's not wound rotor, it's squirrel cage. So if it is a squirrel cage, you should go with which design code you have. If it is design A, B, C, D, it's different designs for the well-known square cage motor. Like I said in the lecture, if it is not given as this problem, you just assume it's B designed. So assume it is class B. That means x1 equals 40% and x2 equals 60%. Keep that in mind. So x1 is 40%, so 40 over 100 multiplied by the given value, which is 47.76, and this give you 19.104 ohms. And x2 is 60 over 100 multiplied by 47.76, and this give you 28.656 ohms. And those are your x1 and x2. Now you have R1, R2, X1, and X2. Okay, guys? That's like what he's saying here. That is now just going very systematic like we just said before. Okay. Now we jump over to the next test, which is the no load test. Okay, guys, for the no-load test, the mechanical speed of the machine almost equals the synchronous speed. It's a little bit less than it, okay? And this means your slip almost equals 0. And that's why R2 over S is very, very high. So you can actually neglect it when compared to the shunt elements. So that is R1 plus JX1, and that is your only shunt element JXM. Don't forget we are dealing with the approximate equivalent circuit here, so we don't have RC in parallel with it. Okay? That is positive, negative V no load, and that is your current going in, which is I no load. Okay? Again, do it for yourself before doing anything. The V no load as given is the rated voltage of the machine, which is 2200 volts. Again, don't forget that's delta connection. That is why V phase, which we want, equals V line to line, which is the given. But the I no load, which is given to you to be 4.5, well divided by square root of 3 amps, again because that is delta connection, so the I phase, which we want, equal I line divided by square root of 3. Okay? And now you can just proceed. You see that the active power P no load from this circuit, it just have one resistor, which is R1. So it is 3 I no load square times R1. But like we said in the lecture, not all the power losses in the machine are just represented in the equivalent circuit. You have at least one, which is the rotational losses or mechanical losses or friction windage losses. They are all the same. But for the approximate equivalent circuit, the core losses also is considered as being constant and just lumped with the rotational losses. Like he said, find me the combined core and rotational losses. That's why we have here another two, which is the core losses P core and the rotational losses P rotational. Those two are not represented by any element in the equivalent circuit, but they are there, so don't forget them. Okay? And he wants you to find those guys combined, so he don't want you to separate them, just find them added together like that. So you just substitute. P no load as is given in the question is 1600 equal 3 I no load square, which is given here to be 4.5 divided by square root of 3 square. R1 we just found it from the DC test, 2.8 plus P core plus P loss. So you can find from here the P core plus P, sorry, that's not P loss, that's P rotational. So P core plus P rotational from this will give you 1543.3 watts. So that's what he wants you to find him, is the combined core and rotational losses. But we still need to find XM. That is why we need to find Q. And I'm gonna again do the same thing, that is P no load equal square root, so no, yeah, it'll make me 3 V no load I no load sine theta no load. Okay, so this guy is 1600 equal 3 V no load is 2200, I no load 4.5 over square root of 3 cosine theta no load. And from here you can find theta no load to be 84.646 degrees. And from it I can find Q no load, because equals P no load tan theta no load, like just we did before. And this gives you 1772.492 bars. Having in mind that Q no load from the circuit, you just have two reactances here, X1 and XM, and they are connected in series. So this guy equaled 3 I no load square X1 plus XM. Okay? Everything is known now. Q no load, we just found it from here. X1 we found in back in your log rotor test. And I no load is 4.5 over square root of 3. So everything is known except for XM. So you can find XM directly to be 823.892 or 982, sorry, ohms. That's what I'm saying all the time. Look guys, XM is 823 something. 823. If we look back at X1 and X2, it is 28 and 19. That's why I'm saying the typical machine RC and XM are very, very large compared to R1, R2, X1 and X2. That's again what I'm saying all the time. Keep looking at the numbers when they come, because they mean something. So if you just doing that and you just line it out, XM to be a very small value compared, so if X1 and X2 in the ranges of 20 and 30, and you find XM to be 4 or 5, that means definitely you're having a mistake, and you have just to log back and see what mistake have you done. Okay guys, so that's the way of doing this with the approximate equivalent circuit, which is much easier than doing it with the exact equivalent circuit. So the exact equivalent circuit, how to deal with it, we'll just talk about this in the next lecture. But yeah, it's not that bad either. We're doing with the exact equivalent circuit, but actually most of the time we're dealing with this approximate equivalent circuit. That's why I'm just focusing on it on this tutorial. Okay guys, now you have all the parameters and you can just use the equivalent circuit to do whatever you want. Okay guys, you can just use it to find all the powers and power losses and calculate the torque, the current, everything in the machine, and we'll be just keep dealing with this the next tutorial, when you just learn how to use the equivalent circuit parameters to just estimate the performance of the machine. Okay guys, before I jump over, let me just try to get you a glimpse of this and have another very simple question for you to solve. So yeah, that's another problem to solve. It's just saying that a 60 Hz 3-phase Y connected induction motor. So it's talking about an induction machine and giving you some information about it. To be 60 Hz 3-phase Y connected, has 4 poles, so number of poles here is 4, so number of poles P small equals 4, and rated speed is 1750 RPMs. So an M, which is mechanical speed rated, equals 1750 RPMs. It wants you to calculate the synchronous speed, that is the first one. So number 8, he wants you to find him the synchronous speed in S, which is easy, 120 F over P. Okay, so 120, and the frequency given is 60 Hertz, number of poles is 4, and that gives you 1800 RPMs. That easy. But by the way, he could even not give you the number of poles here, and still you can solve the problem. How this? Let me just say if number of poles is not given. Okay, because for a motor, for the induction motor, you know that the mechanical speed Nm is less than the synchronous speed, but it's very close to it. Okay, so if you don't have any idea about the number of poles, you just start making yourself a table. So you know that the number of poles for any kind of machine is an even number divided by 2. It's pairs of poles all the time. So it can 2, 4, 6, 8, 10, 12, and so forth. So I'm gonna start assuming that number of poles is 2 and calculating the synchronous speed. 120 F is 60 divided by number of poles, which is 2. That is 3600 RPMs. Okay, and say what if the number of poles is 4? Synchronous speed, like we just calculated them, is 1800 RPMs. What about P equals 6? The synchronous speed is 120 F is 60 over number of poles 6. That gives you 1200 RPMs. And just look about how much speed you have. So the speed of the machine, the mechanical speed, the actual speed is 1750. So you look at which synchronous speed of them is very close to this mechanical speed, but a little bit higher than it. Because like we said, the mechanical speed is a little bit less than the synchronous speed. That's a fact with the induction motor. So it cannot be 3600, that's very high, and it cannot be 1200, that's lower than it. The closest one and a little bit higher than it is the 1800 RPMs. So you can find from 12, that's now 1800, and you now know the number of poles. So if we give you the speed, guys, you don't need even to know the number of poles. You can just find it out yourself. Okay? But here is giving you the number of poles, so it's much easier. You don't need to do all of this, but keep it in mind. It may be a small trick to deceive you sometime. Okay? Sounds good. Number B, calculate the slip speed. Pay attention to what he wants you to find. It is the slip speed, not the slip. The slip speed N slip equals Ns minus Nm. The Ns is 1800 and the Nm is 1750, so this is 50 RPM. That's the slip speed. Okay? Good. Number C, calculate the slip. So the slip is different from the slip speed. The slip S equals Ns minus Nm over Ns, which is the slip speed over Ns. The slip speed we just found to be 50 RPMs over Ns, which is 1800. So your slip is 0.02778. Seeing here the slip. The slip for motor operation, like we said before, is less than 1. And it is a very small value, like we say all the time. The typical value for the slip at the rated speed is very, very small. It is 0.02, something like that. Okay? Again, that's something to look at. For a motor, the slip has to be less than 1, and it's very small, like you've seen here. Otherwise, you're doing a mistake. Okay? Okay. Another question, number D, calculate the frequency of the rotor current. The frequency of the rotor current, like we said before, Fr equals the slip S times the frequency of the stator current. Okay? So, you can just dot the slip, which is just calculated 0.02778, multiplied by the frequency of the stator, which is 60 Hertz, and that give you 1.6667 Hertz. See the frequency of the rotor, like I'm saying in the lectures all the time, that the frequency, the actual frequency of the rotor is especially at the rate speed, which is very high most of the time. Sorry, so that is 1.667. Like we say, it's a very, very small amount of frequency. Okay? And that's why, like I said before, remember when I just having you to look at the power flow of the machine, we just have it like that. P input, which is electrical power going to the stator, and you lose copper losses in the stator, and the core losses, which is actually the P core and stator plus the P core and rotor. They are combined together, like I'm said before. The rest is the air gap power, the power crossing the air gap towards the rotor. You lose P copper and the rotor, and the rest is your P converted, and you keep losing the P rotational, the rotational losses, and the output power here. That's why I'm saying that. Remember when I said the core losses here is just lumped, the stator core losses and the rotor core losses are just added together and just put on the stator side here. Okay, I hope you remember. That is the stator side here, and that is the rotor side here, and between them is the air gap power. So why we are just taking the core losses in the rotor on the stator side and not leaving it here, for example? Because the core losses in the rotor is much, much less compared to the core losses in the stator, and that's why we can just lump them together on the stator side without losing much accuracy. Why? Because like we said before, that the core losses dependent on the frequency. Okay, and like you've seen here, the frequency of the rotor circuit is 1.6 Hertz, which is very, very small compared to the 60 Hertz of the frequency of the stator. Okay guys, so anyways, the core losses in the rotor is very, very, very small compared to the core losses in the stator, and that's why you can just lump them together on the stator side. But it wouldn't be that accurate if you try to do this on the rotor side, or lump them together on the rotor side. That would be wrong. Okay, sounds good. So that's a very, it's a good question to just keep looking at. Okay, and let me just give you some stuff, because he just asked you to find the synchronous speed, the slip speed, and all that stuff. But I'm gonna say it, sometimes he wouldn't just ask you about this. He would just give them names. So the synchronous speed, NS, he can just don't tell you find me the synchronous speed, but rather it find you the speed of stator field. It is the synchronous speed, or the speed of rotor field with respect to the stator. So the synchronous speed is the speed of the fields. Like we said, the rotor field and the stator field, both of them rotate at the same speed, which is the synchronous speed. But that's the speed of rotor field with respect to the stator, because the speed of the rotor field with respect to the rotor body is different. Like we said before, that is the slip speed actually. So the slip speed is the speed of rotor field with respect to rotor body, or rotor winding, whatever you want to call it. So he may not want you or just write it like in the problem, find me the slip speed. Rather, he wants you to find me the speed of rotor field with respect to the rotor body. And you should note for yourself that equal the slip speed, which is the difference between the synchronous speed and the mechanical speed. Okay, guys? So keep that in mind. The speed of a stator field is the synchronous speed, but the speed of the rotor field has two different ways. If you want it with respect to the rotor, then it is the slip speed. If you want it with respect to the stator, then it is the synchronous speed itself. Okay, guys? And that's, an intrinsic question to find. Most of the time you find something like those in the theoretical questions in the exam, because they're just, a short questions to be answered directly, but they need you to be attention, otherwise you may miss some of them. So, that was it. Next time, on the next lecture, actually, sorry, next tutorial, we'll be having problems on the performance assessment of the three-phase induction motor. We use the equivalent circuit parameters we just used in the lab, or just found like a problem like we just solved, and use the equivalent circuit to determine the performance of the induction machine. I mean, finding all the different currents moving inside the machine and finding the different powers and power losses and calculate the efficiency and all that stuff. Okay? Okay. Thanks so much for joining me today, and I hope to see you next time.